Hi there, and welcome to this lesson on Pure Mathematics 4. In this lesson, we're on Chapter 1, 1.1, and we're looking at proof by contradiction. Now, what is proof by contradiction? Well, in many cases, it's very difficult to prove that a statement is true. And surprisingly, a good approach can be to turn this on its head and to assume the complete opposite. So we assume that the statement is false. We then use logical steps built upon the assumption that the statement is false to create some form of contradiction or impossibility. And if we're able to do this, the only flaw in our argument must be our original assumption. This means that the statement we wanted to prove is not false and must therefore be true. This is proof by contradiction. Now, in A-level in particular, there's an important technique that gets used quite a lot. Frequently, we want to consider the even numbers and the odd numbers separately, or we just want a method for talking about the even numbers or talking about an odd number. So first of all, even numbers, they're all multiples of 2. And what that means is that any even integer can be written in the form n equals 2 times k, where k is an integer. And for the odd numbers, they're all one more than an even number, and that means that all odd integers can be written in the form n equals 2k plus 1, an even number plus 1. But this process of writing an even number as n equals 2k, an odd number as n equals 2k plus 1, gets used quite a lot. Okay, let's have a look at an example. Proof by contradiction that there is no greatest even integer. Now, what's that saying? It's asking us to prove that there is no biggest even number, that there isn't an even number which is the largest one, where there is no even number bigger than it. Now, that's clearly true. It's obvious that there isn't a biggest even number. What's tricky is actually writing down the proof in a very formal way, rather than just saying it's clearly true, it's obviously true. And this, again, is a case where it's quite difficult just to prove that the statement is true. It's a lot easier if we assume the opposite thing. So our assumption is, well, actually, yes, there is a greatest even number. And we're going to call that number n. And what we're then going to do is try and create some sort of contradiction or impossibility. In this case, what we'll try and do is create an even number which is bigger than n, which will disprove our assumption. Okay, I'll let you have a go at doing this yourself first. As I say, the tricky thing is just writing down the argument in a formal way, step by step, which they'll be happy with in the exam. But I'll let you have a go, pause the video, come back to me again when you're ready. Okay, let's have a look at this. So we're looking for an even number which is bigger than n, because that will disprove our assumption. Well, the most obvious thing to do is to add 2 to n. So n plus 2, well, first of all, that's an integer. So n plus 2 is an integer and it's bigger than n. In other words, we've already got halfway to doing what we want to do. So we found an integer which is bigger than n. We still need to prove that it's even. It's not enough just to say, well, that's clearly an even number. It's obviously an even number. We need to prove that it is. Well, our original number n, we've said that that's even. So we've said there's a greatest even integer and we've called it n. So that means that we can write n as n equals 2k. n plus 2, the number that we've invented, that will therefore equal 2k plus 2. We can factorize the 2k plus 2 and get 2 times by k plus 1. Now, at that point, you can say that n plus 2 is an even integer because it's 2 times another integer. K plus 1 is itself an integer. So n plus 2, we've said that it's an integer, and we've proved that it's an even integer, which is bigger than n. Well, this contradicts our assumption that there is a greatest even integer n, because we've shown that n plus 2 is bigger than it, and it's even. And the final thing you do on any proof like this is just restate what you've been asked to prove. So you do need to do this. Therefore, there is no greatest even integer. Okay, example 2, a little bit more tricky, this one. Given any integer n, prove by contradiction that if n squared is even, then n itself must also be even. So what that's saying? It's saying that if you've got an integer, if you've got a number n, and when you square it, you get an even number, then the original number itself must also be even. And again, intuitively, that feels like it's obviously true. But the easiest way to prove it's true is actually to assume the opposite thing. So we assume that there is an integer n, such that when you square it, you get an even number, but that n itself is odd. So that's our assumption. We're assuming that there's an integer that's even when you square it, but that the integer itself is odd. Okay, I'll let you have a go at working on from here. So see if you can make your way through this, and then come back to me again when you're ready. Pause the video. Okay, let's have a look. The starting point can often be the trickiest thing with this. So we're going to say, well, if n is an odd number, what happens? So let n be an odd number, and that means we let n equal 2k plus 1, where k is an integer. And then we're going to square it. So if we square n, we'll get 2k plus 1 squared. Multiplying out the brackets gives us 4k squared plus 4k plus 1. Then factorizing the first two terms gives us n squared will equal 2 times 2k squared plus 2k plus 1. But that means that n squared is an odd number, because we've got 2 times by an integer, 2k squared plus 2k will be an integer plus 1. So if n is an odd number, n squared is an odd number. But that disproves our assumption. Our assumption said, let's assume that there is an integer n such that n squared is even, but n is odd. But we've shown that if n is odd, n squared is odd as well. So this contradicts our assumption that there exists an integer n such that n squared is even, but n is odd. And then finally, you just restate what you've been asked to prove. Therefore, given any integer n, if n squared is even, then n must also be even. Okay, example 3. It's quite a lot more difficult to work out yourself. You'll understand it when you're shown the proof, but you'll do very well if you're able to work out the proof. It's a very famous proof in pure mathematics. Prove by contradiction that the square root of 2 is an irrational number. Now, what's that saying? It's saying that the square root of 2 cannot be written as a fraction. Irrational numbers are numbers which it's impossible to write as a fraction. So if the square root of 2 is an irrational number, there's no fraction which is exactly the same as the square root of 2. How do we write that down? Well, first of all, we assume the opposite thing. So we assume that the square root of 2 can be written as a fraction. And if it can be written as a fraction, that means that the square root of 2 is equal to a divided by b for some integers, a and b. Let's go one step further, and then I'll let you have a go at completing the proof. So if the square root of 2 is equal to a over b, it's helpful if we let a and b be the smallest integers, such that the square root of 2 is a over b. Now, all that's saying is, if you've got a fraction which equals the square root of 2, simplify that fraction so that you've got the smallest possible numbers for a and b. So in other words, a and b has been simplified, which means that a and b have got no common factors. Now, what the proof does, the proof says that if you assume all of this, you can show that a is an even number and that b is an even number, and that they do have a common factor. So you create a contradiction. Having assumed that a and b have no common factors, it's possible to prove that a and b do have a common factor, that they're both divisible by 2. Now, I'll let you have a go at working out the detail. As I say, it's quite tricky, this, but have a go, pause the video, and then come back to me when you're ready. Okay, let's have a look at the proof. So that was our assumption. Our assumption was that the square root of 2 is a rational number, that you can write it as a fraction, and that fraction we'll call a over b, where we've simplified the fraction. So a and b have got no common factors. What we do next is square both sides of the equation. So 2 is equal to a squared divided by b squared. Rearranging that gives us a squared is equal to 2 times by b squared. Now, if you remember the last example, that means that a squared is even because it's 2 times by an integer. But if a squared is even, what we showed in the last example is that means that a must also be even. That means that we can write a in the form 2m, 2 times some integer m. We then substitute that value of a back into this equation here. A squared equals 2b squared. So substituting a equals 2m into there gives us 2m all squared is equal to 2b squared. Multiplying out the brackets gives us 4m squared is equal to 2b squared. Dividing by 2 gives us 2m squared equals b squared. But we've now arrived at a very similar position as we did to right at the beginning. What we've shown here is that b squared must be an even number because it's a multiple of 2. But if b squared is an even number, that means that b is also an even number, as we proved in the previous example. So we've shown that a is an even number, it's a multiple of 2, and we've also shown that b is an even number, it's also a multiple of 2. But that means that a and b have a common factor of 2. But this contradicts our assumption. We assume that the square root of 2 could be written as a fraction a over b, where a and b have no common factors because the fraction's been simplified. Therefore, the square root of 2 cannot be written as a fraction, and it must be an irrational number. Okay, the last example is another very famous proof in pure mathematics. And it's the proof that there are infinitely many prime numbers, that they never stop, and that there are infinitely many of them. Now again, it's quite tricky to prove that. What's a lot easier to prove is that the opposite thing can't be true. So we assume the opposite. We assume that actually there is a finite number of prime numbers. And then we write them in a list. So the first prime number would be 2, the second one would be 3, then 5, and then so on and so on. And ultimately, if there's a finite number of prime numbers, we'll get to the last one. And we'll call that one Pn. What we then do is create a new number a. And what we're going to do is show that this number is either a prime number itself, or when you factorize it, at least one of its factors will also be a prime number. There's not much more that needs to be done after that statement. I'll let you have a go at completing the proof. So have a go, pause the video, and come back to me when you're ready. Okay, let's have a look at this. So we're trying to prove that there are infinitely many primes. We're assuming the opposite thing, that there's a finite number of primes, which means it's possible to make a list of them from P1 up to Pn. And then we've created a new number a, which is what you would get if you multiplied all of the primes together and then added 1. Now, the significant thing about this number a is that if we divide it by P1, we'll get a remainder of 1. If we divide it by P2, we'll also get a remainder of 1. If we divide it by P3, we'll get a remainder of 1. In fact, if we divide this number by any of the primes, we're guaranteed to get a remainder of 1. So, what does that mean? It means that none of the primes are factors of this number. Now, if none of the primes are factors of this number a, there's only 2 possibilities. So the first possibility is that a itself is a prime number, which is why it doesn't have any other prime factors. The only other possibility is that you can factorize this number, and when you factorize it, any number that you can factorize into prime factors. So if you can factorize it, it will have a prime factor, which again can't be in the list of possible primes P1 to Pn, because we've said that when you divide by those, you'll always get a remainder of 1 with this particular number. A little bit confusing, that. Anyway, in either case, you have a contradiction of the assumption that there are a finite number of primes. So our assumption is false. If our assumption is false, therefore, there are infinitely many prime numbers. Okay, that gets us to the end of this lesson. If you've got the textbook, then turn to page 4 and have a go at doing some of these yourself. Thanks very much for listening, and cheerio.